Thanks, Robin. Actually, this talk is on behalf of my former student, Tim Pearson, who was unable to travel to present the talk himself. And of course, therefore, I would ask you to reserve the really hard questions for Tim sometime when you get a chance to talk to him. This work is called CloseTalker, and it's focused on making it easy and secure for devices to meet each other for the first time. And it's motivated by the advent of the IoT, the Internet of Things. As all of us know, there is likely to be millions or billions of devices deployed in the next few years or decades. And many of these devices do not have the traditional sorts of UI that a laptop or a smartphone has. They don't have a keyboard. They don't have a screen. Many of them have literally no buttons or other user interface. And so how do you get two of these devices to introduce to each other in order to establish a longer-term relationship or a longer-distance relationship? And we use proximity as a mechanism for them to exchange even just one packet containing a secret key, which they can then use to bootstrap a high-bandwidth long-term relationship. For example, we like to think of a patient who goes for her annual checkup at the doctor's office, and she's wearing a fitness band or something like that that she uses for tracking steps or tracking her glucose. Maybe she's diabetic. And there's almost no UI on that, no way to display this data, but she wants to discuss it with her doctor. And there's a big screen TV right there in the exam room, and so she just walks up to the TV and holds her fitness band within a few centimeters of that television, and then they can exchange a secret key or something like that, and then they can have a high bandwidth, usual TLS over Wi-Fi connection. So the idea of CloseTalker is that we assume that one of the devices has two antennas, and it uses one of those antennas to send a packet that contains that secret, and the other antenna to simultaneously transmit white noise in the same spectrum. That second antenna, therefore, is jamming. This is called friendly jamming because it's done for the purpose of moving forward the original data transmission. Those two antennas are assumed to be a half wavelength apart, and in 2.4 gigahertz Wi-Fi, that's about 6 centimeters. And so what the idea is that the data antenna, the one that's closer to the target, is maybe 1 or 2 centimeters away. The jamming antenna is 7 times farther away, which is proportionately very far away. And so its signal is dramatically weaker, and therefore the target can receive the data signal clearly because it's much stronger than the noise. Whereas anyone who's more than a few centimeters away can't distinguish the data from the noise. And so let's do this first theoretically and then experimentally. How does this work? We can't use the standard Friis equations because we're working in the near field. And so the equations are a little more complicated but well known. How do you model the radio frequency at this range? Let's look at this visually. This is the way I like to think about it. In this plot, you see the distance between the data antenna and the target on the x-axis and the power level at the receiver on the y-axis. And there are two curves here. The blue curve shows the data antenna's receipt power, which is very high when you're close, when that transmitter is very close. And the red curve shows the jamming signal's power of receipt at the receiver. Obviously, when the transmitting device is only a centimeter away, it is very high, very strong signal at the receiver. But as you go further away, such as an eavesdropper who might be all of 7 or 8 centimeters away, they can't distinguish the two. Digging a little more deeply, another way of representing this is as a ratio between the energy per bit and the noise. And this is typically called gamma sub B. This is the way RF people often think about this. And that is, again, you can see this very steep drop-off when the transmitter is very close, 1 or 2 centimeters from the receiver. On the left side of these plots, you can see that that ratio is very high, meaning that the receiver is very likely to be able to receive the data signal despite the noise caused by jamming. On the left side, the jamming signal is transmitted at the same power as the data signal. On the right side, we've actually cranked up the power of the jamming signal by 4 dB, meaning it's 2.5 times as powerful as the data signal to provide additional cover. And obviously that brings these plots down because the ratio has gotten lower, data to noise, signal to noise. But it still seems likely that we'd be able to get that data signal through at close range. Let's take this a little further and think about the probability of a symbol, because data is transmitted as a sequence of symbols, each symbol representing one or sometimes more bits, depending on these different modulation schemes. BPSK is binary phase shift keying, and QAM is quadrature amplitude modulation. These are different ways of packing bits into radio symbols. And the simpler ones, BPSK, have a lower probability of a symbol being received in error because they're simpler, they're more likely to be received correctly. But anyway, as you can see, as the distance increases, the probability of error increases. The desired target receiver is at 1 centimeter or 2 centimeters away. The adversaries, the eavesdroppers, are further away, and they're very likely to experience an error in receiving a symbol. Now, of course, we don't care about symbols, we care about frames. What we want to know is, what is the probability of a frame arriving successfully? A packet is in a frame. And in CloseTalker, we imagine this being used for only a few packets. And so now, higher is good, higher probability of success. And on the left side, again, the jamming signal is the same power as the transmit, the data signal. And for any receiver within a few centimeters, the probability of that frame getting through is very high. But any adversary who is further away, the probability is basically 0. So we're going to focus now on BPSK because that's the simplest modulation scheme, the most likely to succeed. And I'm going to shift to an experimental plots now. Here we have used an SDR to transmit the data out of one antenna and a white noise jamming signal out of the other antenna. And we used 4 off-the-shelf different antennas to receive that signal. And we transmitted 1,000 packets for each experimental condition and are showing the average here. And the top graph, the top curve on the graph, is the probability or the ratio, the fraction of frames received successfully over all those cases when there was no jamming. Notice it's not 1. And the reason is twofold. Real life is never perfect. There's always ambient noise. Some frames aren't going to be received. The other is that our theory that we were just looking at didn't account for all of the details of near-field effects. And at this range, we are dealing with near-field effects in radio. And so there will be some loss or lack of reception due to that. So about 60% of the frames are received even without jamming. But once we add jamming, you can see this drop off, as in those other curves we saw before. We're likely to get about 40 to 50% of the frames through at close range, but then beyond 7 centimeters, none ever got through. And so again, the idea is that the target can receive it well, and the adversaries cannot. Now, of course, we need it to be better than 50%, so you might send the frame a few times to make sure that at least one of them gets through. Here's a plot showing, suppose you sent 3 copies of the frame, and all you care is 1 gets through. What's the probability of success? And now without jamming, it's close to 1. With jamming at the same power level, the red curve, it's close to 1 for the receiver at the 1 centimeter distance, but for the adversary beyond 7 centimeters, they never receive it at all. So you might think, okay, what if the adversary is tricky and uses a directional antenna? So you have 2 antennas that are being transmitting. One is transmitting the data. That's what the adversary wants to receive. The other antenna is transmitting the jamming signal. The adversary would like to ignore that. So if we can focus a directional antenna on the data transmitter, maybe we can pick up that signal. But it turns out if you do the math, with an adversary all of a half a meter away, which is not very far, they would have to have a directional antenna that can focus down to about 1 degree or 2, which is extremely narrow lobe and almost impossible to produce. Another approach the adversary might do is to mathematically separate the signals. So you're getting this blend of the data signal and the noise signal, and you want to separate them and pull out the data. It has been shown that you can separate signals like that if the channel matrix has rank greater than 1 and is well conditioned. A group led by Tippenhauer showed this, but they only showed it for a low frequency signal, 900 megahertz, I think, whereas Wi-Fi is a higher frequency signal, and they only showed it for a very simple modulation scheme, frequency shift keying and not BPSK. Nobody's been able to demonstrate that ability to separate in practical conditions for Wi-Fi. And so we believe, as with most security solutions, what we've done is raise the bar to make it very difficult for an adversary to intercept that data packet that these two close devices are using to establish a relationship. So in summary, the nice thing about CloseTalker is that I think it's a very convenient and fast and easy way. It's very intuitive. You hold two things next to each other and you press some kind of initiate button and they transmit a few frames. That takes a few microseconds and now they are paired or partnered or have some relationship. They can use that secret that they exchanged to bootstrap a traditional TLS over Wi-Fi connection or over the internet, what have you. It doesn't require any hardware modification, and we're using just the physics of radio to protect the data. That inverse square law is what is helping us do this work. I think it's going to be most useful for these kinds of user-intended ad hoc encounters. You take two devices and say, I want this light switch and this light bulb to know each other and to work together. I want my fitness band and my treadmill to work together. I want this remote control and this television to work together. And I just hold them together and push some sort of a button or speak some command to tell them to initiate that relationship. Sometimes when I talk about this work, people think, well, this is only useful for really short-range connections. It's not going to be able to transmit a lot of data, and it's not going to work over long distances. That's not the point. The point is to initiate that relationship, and then they can establish a long-distance or long-term data transfer. Another thing people hear, they hear the word jamming and they say, oh my gosh, you're flooding the Wi-Fi network with noise. That's going to destroy everyone else's communication. Well, just remember, we only transmit that jamming signal during exactly the same time we're transmitting the data signal. We're sending a data packet. That obviously uses up the channel, but that's true for everyone else's data packets when they transmit as well. We're not adding any additional interference beyond sending data. There's no extra hardware here. We're not assuming the existence of NFC or adding it to every device or some other type of radio. We don't require pre-shared secrets. In fact, that's kind of the purpose of it, is to make that happen. And we don't need any complex crypto. There's no fancy math involved here. It's just sending a packet in the clear and hoping that, or expecting that no one else can receive it. In fact, kind of a cool thing, the target device doesn't even need to know that CloseTalker is being used. It just receives a packet, just like normal. So it doesn't need to do anything special except receive that and then presumably use that key or address secret to start a communication. So that's the gist of it, and I'm happy to answer any questions you might have, or I encourage you to contact Tim, tjp@cs.dartmouth.edu, if you have deeper questions. Thank you.